right, we should get going here. This is going to be this could be a long evening. I'm going to try to make it efficient, but
Right.
so some of you I know have worked on this before, the doubling of the cube, right?
A little bit.
A little bit. All right. Okay. Well, you know, as the first thing to think about is, why would a political organization be concerned about such a thing as such an esoteric geometric problem? And it's useful. I actually thought about, well, what practical use could you have with doubling a cube? And I had a hard time thinking of anything. The thing I came up with, maybe you're a bartender. Somebody orders a scotch on the rocks. You give them the ice cubes and scotch, right? And then somebody orders a double, and you got to do everything twice as big, right? Anyway, I couldn't think of a whole lot of things, but obviously it's not so much the practical thing. There's a story that Plato told about the Greek inhabitants of the island of Delos. This was about 80 years before Plato. And there was a plague in this island, and the Delians were getting totally freaked out about this, and they went to the oracle and asked what they should do. And the oracle's response was to double the size of the altar. And the altar was a cube. So they were really puzzled by this. And Plato, later on straightened them out and said to forget the magical interpretations of the oracle's demand and concentrate on actually solving the problem. And that this is a pedagogical exercise that develops the mind. And so there's something that, Lynn emphasizes the doubling of the cube. He refers to it frequently in his writings. And it's related to the idea he has also emphasized a lot more recently, the vicarious hypothesis of Kepler. And I'll just read a short thing in one of his recent papers. He says, a vicarious hypothesis is not a physical object. It is a manifest creation crafted according to the design for a shadow of reality, not the reality itself. It is, as Kepler defines the matter in his practice, a special kind of efficient shadow of reality. It is not something intrinsic to nature in the sense that the errant dogma of sense perception proposes. It is a comprehension of a shadow truthfully cast by reality upon the mind. Now, he had earlier discussed this idea referred to by Riemann as Geistesmasse, or mental objects. And I'll just read a little of what I say here, because it's kind of situate what we're going to do with the doubling of the cube. He says, the concept of Geistesmasse is in fact the pinnacle, subsuming concept of all European science, from Thales and the Pythagoreans through Riemann and beyond. It corresponds functionally to Plato's rigorous definition of the concept of the idea. I begin the elementary introduction of this notion of unseen but fully efficient mental objects by comparing a selection of such mental objects. Number one, the functionally decisive but unseen aspect of Archytas' unique solution to the Delian problem. 2, Kepler's conception of gravitation. 3, Gauss's method of his discovery of the orbits of key asteroids. And 4, Leibniz's cohering concept of the monad as coordinate with a universal principle of universal physical least action. So then he elaborates more on this idea of 2 classes of mental objects, those that deal with the physical world and those that deal with the way the mind operates. So as we work through this, as we go through the specific steps in this process of doubling the cube, we want to at all times keep in mind the whole. Keep in mind the whole concept of what we're creating. Hang on 1 second here. Because the way we're going to look at this is looking at Archytas' mind. What we're going to try to hypothesize what was actually going on in his mind. Well, I had something else. Anyway, now, Mark, how's this going to work?
What are you trying to do?
Well, I have things that I hear I need to pull up on the screen.
That's fine. You can do it.
You
It
can
doesn't
minimize
matter.
that.
Leonardo can still see you.
He can still see me. Oh, okay.
Yeah.
Okay, good.
You just don't X out of it. Just
Right.
minimize
And I also have diagrams on the PDF file so I
Yeah.
can see,
Oh, okay. All right, good.
but I have to know which page.
All right. So it's the first one on the list.
Be looking at that.
Yeah, the one that's labeled AAA.
He's got the PDF, so it's just the first page.
So the ones with the AP, BM, and there's like a red circle, right?
Green donut.
It's got the
Green.
yeah, it's got the torus, the cylinder, and the cone.
It's a green donut, a blue cylinder, and
It's the only one that is red colored, I think.
a red
Yeah,
cone.
that's the first page.
Right.
Got it.
Yeah. Okay. So this is just to confuse people. I mean, this is as people may know, some may not, but Archytas, the way he solved the problem of doubling the cube is with his construction involving a cone, a torus, and a cylinder. And if you're like me, you look at this thing and the first thing that goes through your mind is, how the hell did he come up with this? What does that have to do with doubling a cube? And even if I did see, well, how did he come up with it? How did his mind hypothesize such a thing?
He was thinking over it with coffee and donuts, and he had the coffee filter.
Okay, well, maybe so.
It sounds like a bad myth.
But actually,
Like you with the apple on the head.
yeah. Hang on a second here. So what we're going to look at is, how Archytas actually would have, he would have had, in a sense, a whole language that he was familiar with. He was an expert geometer, and he was also, we assume, there's a lot we don't know about Greek music, but one would presume that he was involved in music in some way. And the way to think about this problem is, think of performing Bach's B minor Mass. To do it well, you need to be, you need to attend to where you breathe, keeping the voice elevated, the timing, pitch. But at the time you're very conscious of these things, you're also keeping in mind the piece as a whole and how these things generate the whole. So in working through this night, we're going to try to keep in mind the intention of the whole. So what we're going to go through is a few things that would have been kind of, basic to Archytas, that he would have known to start with. It wouldn't be foreign. A lot of them may be a little bit foreign to people here. People probably have a little bit of familiarity with them. But what I want to do is introduce two concepts. One is similar triangles. And let's see, where am I? Oh, I've got my markers over here. Okay. So let's say you got one triangle and you have a bigger triangle, but as you can see, there's something similar about them. They have the same essential shape, and you can define that rigorously. The angles, this angle is the same angle as this. This angle is the same angle as this, and this angle is the same angle as this. So in any angle, any triangle of that nature, any two triangles that share that are said to be similar. And just as a note, we are at this point dealing with certain assumptions about a flat surface. In which case, if you have two angles that are the same, say this one's a right angle and this one's a right angle, then that's all you need to prove that it's a similar triangle. And the other one will also be the third angle will also be similar. Now, what's also crucial is this idea of proportion. If you have that, let's compare this length. Let's call this length A, this length B, and this length C. And we'll call this one capital A, capital B, capital C. So,
Anyway, we can read the correct light from the board.
well,
We like this one.
can we have one of them on?
That might, it's fine for the
How about-
camera here, but it might be bad for Leonardo. Leonardo, can you see?
Can you see that all
I
right?
can see. It's better with the top light, because if you have both lights, it's too much illumination.
But with one light, it's okay?
Yeah, the top one.
Okay, all right, well then,
Turn that light off. That would be good. No, they're all.
they're all together.
Which one? We can maybe turn it with that one. No.
No, it's talking about that one.
Yeah,
Oh,
she's talking about-
no, that one's bothering me.
Well, I don't know, we may have to live with it. Because we got to keep moving here. Got to keep moving. What you'll in these similar triangles, if you compare this length to this length, the growth factor, let's say, or the multiplication factor you get from here to here is going to be exactly the same as to get from here to here, or to get from here to here. That is, the amount you expand this to stretch it out to here is the same factor, the same proportion as you extend this to get to here. Um, let's see, what else we could say about these. I mean, there are other things you could say. Well, another thing is, if you make a ratio of this length to this length, A over C, it's going to be the same as the ratio of big A over big C. And I mean, another way to look at it is you can put this one inside this one, you know, just like that.
I think you have to use a colon. I don't know if that matters much.
You don't need to.
Because it's equal sign is equivalence.
Yeah, it would be if you measure the length of this and the length of this,
The
that ratio is going to be the same as.
Yeah, but that's
That ratio.
denoted with a colon, I'm just saying.
All right, well, let's not worry about
New
it.
people.
I think people get the idea. So let's see what else we need to do on similar triangles. Okay, so is that pretty clear? Similar triangles? People have any
Yes.
questions? We'll get into some cases where it's maybe not so obvious, but the next concept that would have been kind of basic to Archytas' view of the world is the idea of a geometric mean. And here we're going to work through some things. Put something else up on the screen here. Cubes. Here we go. All right. Can people see this?
Right. Two different triangles.
Can people see this up here?
No.
The boxes, you don't need to read. Is the boxes visible? Are the boxes?
Yes.
Okay. So if you have a square and you double it, you get two squares. Okay? And then if you double it again, you double the two squares, you get four. Okay? That's not so complicated. What if you start out with 4 and you add half of, you have 50%. Okay? Then you get this. Then you add 50% of this. That's like adding 3 more there, and then you get this. Now in this one, you had a growth factor of 2, multiplied by 2 to get here. You multiply by 2 to get to here. Here, the growth factor was 1.5. You multiply by this by 1.5, you get there. You multiply this by 1.5, and you get to there. Okay. So the idea of geometric mean is the step in the middle. They call it geometric mean. In this case, it's the 2. In this case, it's the 6. And for Victor's benefit, we now have colons in between the numbers here.
Either way.
That looks like a multiplication sign to me, but
Oh, well, that's,
This is really
you can't see the dot there.
I can't even really see it.
You can't see it.
I don't have a problem.
Oliver can't see anything.
All right.
We'll get you a copy of it later.
I don't know if I can make it bigger.
You can.
I can?
You
For
can just
the-
hit the plus.
The plus? Yeah, all right.
What do you think about this?
Let's see if it works here. Yeah, there we go.
Like that, Mr. Mulberg.
The problem is Leonardo doesn't have any of this.
Yeah, well, you can, you know what we're looking at now? It's the one called cubes.
I don't think he has that.
When will you expand? If there's two, then it's four, then
Well,
it's
It's
four,
like
then
it's in
it's eight.
between this, that's what it's.
Right, two little squares.
Oh, they're
Then it becomes,
equal.
then it multiplies, right?
Yeah, yeah. And then the next one is the 4 squares. It becomes 6, and then it becomes 9.
Then it creates dimensions, right?
But they're not equal though.
Well, it creates a square of 9.
They share common.
little squares.
But none is one or the other.
So you got the right one, I think.
Between this relationship.
So
It's not big, but, because there's two triangles, so that's the way to be similarities.
now,
And there's this thing that they both share in common, which is something similar.
the point is, if you go to school, they'll talk about geometric means, all in terms of numbers. Like they'll say,
I guess if you leave the world of numbers,
if you say, between 1 and 4,
I mean, there's still two.
there's a geometric
It's like
mean
you said, you
of
like
2.
maybe- I said we're still in a two-dimensional realm.
Okay. So, they put it all in terms of numbers, or another way to put it is this 1 over 2 equals 2 over 4. But the idea, it's useful to look at it geometrically where it actually comes from, because it is this idea of, in a certain kind of way, being halfway between, the 1 and the 4, or between the 4 and the 9. So, and anyway, there's a lot that could be said about that, but let's just go on.
So you're saying the geometric mean between 4 and 9 is 6?
Yeah.
Okay.
See, that's the whole idea. If you multiply this by 1.5, that means adding that, and that gives you 6. Then you multiply this by 1.5.
Right.
Take each.
So you would say those relationships are equal.
Yeah, what you did to get to here,
Growth.
in a sense, is the same as what you do to get from there to there.
Uh-huh.
Okay.
That makes sense.
And that's going to be important in what we get to with this idea of, there's, you can think of, I find it useful to think of a growth factor, a multiplication factor to go from here to here, and then the same factor to go from here to here. Okay, so now we're going to go to cubes, because you can do the same thing with cubes. And okay. So here you go. Start with 1, multiply it by 2. You get, and then you multiply this by 2, and you get, see what that is? That's not a cube, that's just 1 block deep, 4 blocks, right? You've doubled 2 and you get 4. Then you have to double that again to get to the cube. So instead of two doublings, or as you have the squares, here you have 3. You have 3 growth factors. And then you can look at the next one, where the growth factor is 1.5. So here we're starting with a cube of 8. That's supposed to be a cube. It doesn't look much like a cube, but that's what it is. And then you add 50%, and you get 3 this way, 2 this way, 2 this way. Then you add 50% of this. It's like adding another layer on top. And then you got to make another layer deep. and then you get the cube. So you're doing the same. You multiply by 1.5, multiply by 1.5, multiply by 1.5. So in this case, and this is not doubling the cube, but in going from one size cube to another size cube, there's a two intermediate steps. They're two means. So, any questions about that?
Is that the case with every cube? Two means?
Well, anytime you're making in this kind of multiplication process to get from one to a bigger one.
And it's never one mean and it's never three means? with
That's
cubes?
right. That's right. It's always two.
On your
Um,
top line there, I'm lost. It looks like you're growing from a 2 cubes to 4 cubes to 8 cubes. You're still at the 8 cube. I
Yeah.
don't see any increase.
Well,
One cube to start off.
you started off with 1, you doubled it to make 2,
Maybe you're
Oh.
not seeing.
you doubled it again to make 4,
Okay.
you doubled it again to
I'm
make
vision.
8.
Okay.
Okay?
One was too small.
All right. I see.
Double that cube 3 times.
See, I did get some sugar cubes. They're a little bit,
Let's put in some sugar cubes.
All right.
you know, they're.
Be up all night too.
Okay, so, what's that? Oh.
So that's what you were doing all night, Hunter.
So anyway, you start,
This is a missing element of our
Hunter,
Caius'
can you
thought.
move some of the other, Hunter, can you move some of the other things from your?
Sure.
Oh,
there?
yeah.
Yeah, the coffee cup.
Yeah. Okay.
We all get some sugar cubes. Play with them?
Well, I think we'll have a little intermission where people can play with these things. Although, actually, they're enough. I can,
Pass one around.
yeah, we can. I'll just take a bunch of.
Now, you're sure that's just sugar, right?
Well, I haven't actually eaten any of it.
So you can't skip that intermediary step. You can't go from 2 to 8.
Well, I mean, you can do it, but it's kind of a mystery how you get there. It's not, you know. Here there's kind of a knowable process of growth. So, you know, you can,
You wanna share some sugar cubes?
Leonardo, maybe you can see it this way.
Sure. Okay, not that.
Yeah, you start with 1. You double it.
Alright, so it's grown on the side.
Yeah, you add 1 on the side. And then you double this by adding 2,
So it's 4.
right? And then you double that again, like that.
So now we have a cube.
That's right. You started
And then you have
with,
to double it. The more you put it, it's more increasing.
right. Now,
This is sugar cube.
if anybody says, you know, they can double the cube, you know, you can say, wow, I can octuple the cube. So there.
Divide twice.
So, anyway, so there's that one. But then the other thing, you know, suppose you start with the cube of 8,
Okay.
okay? Then you add, I mean, this is just, I mean, there are many variations you could do on this, but here's, you can add 50%. You add that way. Then to add 50% is like adding one of these. That's half of what you got. So you add 6 of them. You get that. Then you add 50% of this, which is one of these. And I don't have enough to do it, but I think you get the idea.
So it seems like what you're doing is you're taking this unit cube, this one, and you're then figuring out ways to, what are the other cubes that you can create based on that one?
Right.
And how do you get there? Like how do you grow, extrude from that original one to get to the next size cube? And then how do you get from there to the next size cube?
Right.
And it seems like there are certain natural cubes that you find, like the cube of 8 and the cube of 27, right?
Right.
But those are the only ones. So you have 1, you have 8, and you have 27.
Well, those are the whole number ones. Now, what we can expand on that idea. And, let's look at a different example. Well, let's look at a different example here. Suppose you wanted to have, say you got a cube here. Now you're going to, let's say we want to multiply it not by 2 or by 1.5. Let's do it by 1.1. That's going to be our growth factor. Okay. Now that's a little more interesting problem here. So you're going to have this length. Yeah, that is your growth factor is going to be 1.1. So you're going to end up with something like a little bit longer on it. Something like that. But the other dimensions are going to be still 1. So you added, that's more like 1.2. Let's go 1.2. Okay. So you take your cube and you add on one side 2/10 of the length. Okay?
Okay.
Now, we're going to take this, and we're going to multiply that by 1.2.
Oh yeah.
And we're going to, this time we'll put a little layer on top.
Oh, okay, see. Y times 1.2?
Just picking
Just
arbitrary
picking
numbers.
a number that's,
Just that you can always create a cube by those,
Oh,
by any increment you choose, right?
yeah.
But the question is, what will be the total volume of that, right?
Yeah, well, that's what we want to look at.
Well, it's not a cube in the sense that it has equal sides.
It will be.
Yeah, because then we got
What
to
the means, these.
Yeah, no, yeah, each of the means are not, yeah.
do, right, but they weren't equal size over here either.
Yeah.
My point.
Yeah, okay. So anyway, this diagram's not that good, but you can probably get the idea. Because now what we did was we added on this side, and we added on top, and now we got to add
in depth.
the back there. Yeah.
Yeah, sorry.
So anyway, that's you could see the original one is somewhere right there. So, we can, and then if you wanted to do the calculation, you can multiply 1.2.
You started with 1,
Yeah, the volume of this is 1.
and then you multiplied.
The volume of this, is 1.2, because you've added that much. So the volume of this is 1.2 times 1.2. And the volume of this is 1.2 times 1.2 times 1.2. Now,
What is that?
did that solve the problem? Did it double the cube?
I don't know.
Anybody you got their calculator? You can figure out what that is?
Yeah.
Because if it's equal to 2, then we did it. Then we can go home early.
2 times 1 point.
Not
Two
constructive geometry.
1.2, no, it is not 1.728.
1.728. Okay, so that's not big
That
enough.
is wrong.
Okay. All right, so we got a little more work to do.
Let's try 1.3.
But this is the idea that there's you can kind of get the idea that in order to make this exactly double in volume, that one, there's some
Side.
factor that we want to find, and it's going to be a little bit bigger than 1.2. It's not going to be as big as 1.5. So you can.
Boy, working like this.
Whoa.
So this is one of the things that, I think before Archytas, this guy named Hippocrates of Chios, he determined that the problem of doubling the cube really is kind of a projection down to this issue of finding out what is the growth factor, what is the geometric mean. If you can figure out what the geometric means are between a volume of 1 and a volume of 2, then you'll know the crucial thing to build your cube is what this length should be. So the problem reduces to, if you want to think about it, reduces to this idea of finding two means between two extremes, as they say. So,
And if you find one of them, then you kind of automatically find the other, right?
yeah, it's if you find one of them, it's pretty easy to, because you just got to double what you
That
got.
was Hippocrates then?
Yeah, I don't think it's the same one as the medical doctor. I think it was a different.
Hippocrates of Chios.
Right. Now, this idea of two means between two extremes.
Maybe he was trying to cure a plague too.
Here's this may help you understand this idea.
Yee.
There you have two means between two extremes. Okay.
Interesting.
Okay.
I don't know, we should put it in.
So, all right, let's go back to Archytas' mind. He's familiar with these ideas, the geometric mean idea, the similar triangles idea. Those are just kind of basic. Another thing that he was very familiar with is this idea of creating surfaces out of, or creating lines out of points by moving the point, creating a surface by moving a line, and just just a couple of examples. If you have a circle, all right, now you move the circle along its axis, or on, create an axis along where the center is. Then you can see you'll create a surface, right? Right? Create a cylinder. What if you rotate it? Rotate the circle around this axis, the sphere, right? What if you rotate the circle around the edge, a point on the edge? You create an axis here and rotate the circle this way.
Bagel.
Bagel, right.
What?
That's true.
Yeah, you got a torus. Okay. So, I mean, this is something that would have been absolutely basic to Archytas. Another one is, suppose you have a triangle, and you rotate the triangle around one of its sides, like so.
Capsizing for
What do you got there?
Coffee filter.
All right. You got a cone. Okay, now here's another one. You got a different cone if you do a different triangle. Okay.
A smaller one, but
Yeah, yeah. Can you see that? It's just,
yeah,
you just got
it's
it.
forming. It's like forming something else.
Yeah, it's forming a surface. You want to think of the
Mhm.
surface that's being created. And this
An
one just,
invisible surface, though.
well, this one is just a different, I'm just demonstrating two different ones. You could have all different ones. Or you could, well, I guess it's the same thing. If you hold it at the point, you're just rotating it like this. So, anyway, this idea, and also the idea of intersecting surfaces, creating a line. You think of, think of two spheres that intersect. What do you create if you have two intersecting
Circle.
spheres? Yeah, you got a circle. Right.
Oh, two spheres intersecting.
Right.
Oh, okay. It's like I was thinking two circles. I was like, no.
Or what if you have some people are probably familiar with, suppose you have a cone and you intersect that with a plane. There are different kinds of planes, different angles. You got different, you can get a circle, you get an ellipse, you got a parabola. But these are the things that would have been part of the kind of like the language of Archytas. This is what he's familiar with. He knows how these things work. He's got all kinds of ideas. So when he's confronted with any problem, just like a composer, like Beethoven or somebody, they're very intimately involved in these scales, these, modes, the ranges of different instruments. It's like that's part of, what's in their mind. So creating a musical idea, they've got this kind of in their background. And we're in a certain sense handicapped. We're not, we don't think about these things all day, so we kind of got to get our creaky minds working on these things. But this is the kind of thing that would have been basic to Archytas. Now let's proceed. Actually, I have a short little reference here to Lynn in a NEC meeting back in January, I think. He said, the instruments of artistic composition are the most essential aspects and sources of science. And in one of the weekly reports, I think it was, Jason brought up this issue of the scientific method. And what they teach in school is the scientific method. You make a hypothesis, you test it, and you test it, and then you prove it's true. Well, but as he brought up, the crucial is, well, where did you get the hypothesis to begin with? And it's only a mind that's steeped in great music and geometry that you're going to be able to kind of come up with hypotheses that have some likelihood of being useful. So, all right, let's get down to the business here.
Where did the hypothesis come from? That was a very good one.
What was that?
That was a very good one. Where does it come from?
Yeah, that's the critical question.
Intelligence is questioning everything, and knowledge is the answer.
What was the question?
Intelligence means asking the right questions,
Oh,
and
yeah.
knowledge means finding the right answer.
Okay, so here's the kind of the basic construction we're going to look at. In a circle here, and this is another thing that would have been kind of ABC to Archytas. If you draw a triangle inscribed in a semicircle, this angle is always going to be a right angle, no matter where you do your triangle. So we're going to look at the we're going to look at this in a little detail. Let's call let's just put O here, A here, and P here. Now, if you drop a perpendicular line from here down to there, we'll call that Q. Now we have some, that's not a very good line there, but
Opa, yeah.
we have some interesting similar triangles. Okay, let's look at the big triangle, OA, AP, PO. Okay. Now, where's a triangle? Another triangle that's similar to that.
AQP.
AQP. Okay. Let's see. It's got A, the angle at A is the same in this as it is in this. And the angle here is a right angle, just as this is a right angle. So it's got two angles the same, so it's similar. Does everybody see that?
Sorry, which one is similar to which one?
Okay, we're looking at similar to the big triangle.
So OPA.
OPA is the big one, right? And what Michael was saying is AQP is going to be similar to that.
Okay.
OQP also.
What was that?
OQP.
OQP, yeah, OQP is also going to be similar. And that's the one we're going to look at.
OPA?
Well, they both have this angle, right? And they both have a right angle. This has a right angle here. The confusing thing is it's kind of, you have to flip it over to make it look similar. But OQ corresponds to OP. And OP corresponds to OA. Is that clear? So,
Cool.
now, think of what it means here. We've got OQ. If you compare OQ to OP, that's the let's see, what should we call this? We'll call this the shorter side, this the middle side, and this the hypotenuse, just for convenience sake.
Are you gonna label? I guess you don't need to label the sides. I guess you can just call them
Well,
OP and whatnot.
Yeah, well, let's just do that. But in terms of the triangles, you know, this is the short side. So the short side of OPQ corresponds to the short side here. The hypotenuse of OPQ is OP, the hypotenuse of OAP is OA. Is that clear? Okay. So what we can make, what I'm getting to is we have something interesting here, which is a a geometric mean. Because if we look at OQ and OP and OA, what's the relationship of those three? OP, oops, no, we want OQ to begin with. OQ, that's a small one. OP and OA.
Proportionality.
Yeah. What proportionality is interesting?
The fact that there's 3 factors of multiplicity. Interesting.
Isn't OQ to OP as OP is to OA?
Exactly. Let's write that down. It's to be OQ is to OP. That is, this length has to be expanded to this point the same way OP is expanded to be OA. As the ratio of OQ to OP is the same as the ratio of OP to OA.
The ratio between OP is the same as OA, right?
Well, the ratio is between two things. One, the ratio of OQ to OP is the same as the ratio of OP to OA.
Okay.
That's because they're similar triangles.
Because they're similar triangles, right?
Alright.
So by what we looked at with the blocks, OP is what's called the geometric mean between OQ and OA. So this idea of geometric mean, we're going to use that a lot in this.
The line is the geometric mean.
What's that?
The line between,
Not the line. The line OP. Yeah. Actually, technically, it's the length. The length of the line is the geometric mean between the length OQ and the length OA. Now we can add to this another complication. Let's draw a perpendicular from OQ up to OP. And we'll call this B. Now, as you can see, there are more similar triangles.
Right.
And you can see that OQ is now going to be the geometric mean between OB and OP. Is that anybody having trouble with that one?
What was the basis of drawing, of making the line BQB or BQ? Yeah.
You draw this from here perpendicular to here.
You should just put a right angle.
He
there.
wants to know why.
Why?
Yeah, that's it.
From that point.
Well, because
Okay, I got it.
what we're getting at,
Because
keep in
OP
mind,
is the mean between OQ and OA.
yeah. And see, remember what we're kind of looking for is two means between two extremes.
If I get two means between two extremes, machine.
That's right. That's what we're creating.
Wow.
Oh, machine,
This
oh,
is beautiful.
mechanical.
We're getting close.
Yeah. So here, see what we got. We got, if you look at OB and you look at OA, those are the lengths. Those are the two extremes, and we got two means between two extremes. So it's getting interesting. But we haven't quite solved the problem. because we'll have the problem solved if we can make this construction such that OB is exactly half of OA. That is, if we see, we can move P around anywhere we want. You know, we could draw in like this. Let's put P up here. Q will be here. And B will be here. Now that's looking closer to being where this is. See, we're looking at OB and OA.
So OB should be half of OA. So OB would be your 1.
Yeah, if you
OA would
this,
be your 2.
right.
And you're trying to find a OP or a PA, which would be,
Well, O and A are fixed, but you want to you're kind of moving P around, and everything else adjusts according to where P is.
right. But if OB is 1 and OA is 2,
Right.
what line is it that you're looking for to be the mean between the extremes?
Well, OQ is the first mean, OP
Okay.
is the second mean.
All right. Oh, yeah,
So-
you have it written.
Yeah, so in terms of the, going back to the idea of doubling the cube, to get the length of that side of the cube, you want the first mean. The second mean would correspond to the area of the,
So then the question becomes, where do we put P so that we know that OB is exactly half
exactly,
of OA?
exactly. Okay,
And there's an infinite number of possibilities.
that's true. But this is the thing, you know, you can think of, Archytas would have been looking at this with all his insights into geometric constructions. And, you know,
I wonder, sorry, quick question. Earlier, just before you said OB is to OQ, is OQ is to OP?
yeah, yeah, right.
So,
Actually, I need to make a quick public service announcement. I know I have my car in a garage and you can move it right now,
Uh-huh.
but I'm not sure if other people do. But if you do,
No, you don't need to move it unless they have the key.
well, the one underneath
Stays
the
open only.
freeway stays open. It says.
Oh, that one, that one.
Yeah, that one you need to move it.
All right.
I thought you meant the one that we have
No,
to
I
take
gave it
somewhere.
Okay. So, yeah, we could put the other one in here, just squeeze it in, OB over
Try moving over here.
OQ. And if you wanted to, you could continue this process. You could, you know, you could draw a perpendicular here, extend this up, make another similar triangle. I mean, these are the kinds of things that Archytas would have played around
Yeah.
with.
Sure.
As a child, you probably did that.
But one of the things he did have a real sense of this idea of motion, of you know, moving P. Actually, I have a little.
So just to, one question, just to
Yeah.
make sure, so OB would be the side of side of the length of one of the cubes if it's 1. And then
Yeah, if-
A would be the double,
OA would be,
the length of the cube.
well, actually, yeah, see one thing that actually should be noted here, I'll get precisely back to your question, but
So I was just going in and out. real quick.
yeah, we're using numbers in a kind of loose way. Because you were using numbers to describe lengths.
I know, I'm not asking
But-
about the numbers, I'm just saying the length. OB would,
Yeah,
But as a-
yeah, I know, just hold on a second though, because I want to make this caveat before we get to that.
okay.
If we're talking about, you know, when we were doing the squares and cubes, you know, we were talking about numbers applied to lengths as well as to areas as well as to volumes. And that's kind of a sleight of hand, because if you multiply two lengths, you know, you're multiplying two lengths, I mean, who gives you the right to say this is an area? You know, I mean, this is something that's useful to think through, because it's something that they kind of brush aside in most geometry classes, but it's a very relevant.
Wait, what gives you the right to do what now? What did you say?
To say a length, a number applied to a length, you're measuring a length. But now we're going to use numbers also to describe areas or describe volumes. And you know,
That's where it breaks down.
there's a fundamental philosophical issue involved there, and it's useful to at least make a footnote that we're making a certain assumption here that another time, another place could be cleared up.
Meaning like a length of 2 is not the same thing as a volume of 2.
Exactly, yeah. I mean, you multiply 2 times 2, you know, and you got 4. But if you multiply 2 inches by 2 inches, you know, to say you have 4 square inches, that's an idea of geometry. It's not just simply a mathematical concern. Now, your question was about the OB and the length. Yet, what we're looking for, if we're doing the cube, say this is the doubled cube. Our original was 1. How to construct this? The critical thing to know is how long is this length?
Yeah, I know that.
Okay.
You're not listening to me.
Well,
So OB would be, is as if it's that, the side of the length of the.
if this were such that this was half of this,
Okay.
then OQ would actually be this length. OB would be 1, OA is 2. It looks a little more like there. But OQ, this is the first geometric mean. OP is the second one.
What are you saying OQ would be the length of the side of the cube? Of the double cube?
The already double cube.
Yeah. It's
Oh yeah, okay, because it's the second mean, or it's the
the,
first
fir-
mean.
the first mean, yeah.
Yeah.
Okay. Now, let's look at a few things up here. What time is it? Okay, we gotta keep moving here.
Oh, so it should actually be OB is to OQ is OQ is to OA.
No, because you need 2 means in there.
Okay, so it's OB is to OQ is OQ is to OP.
Right. As OP is to OA.
And as OP is to
Right. So here's a nice colored drawing of this. Well, it's a little weird. Maybe it's not so nice. Forget that one. Now I have a moving one. Let's see if this works. It may not work in this.
Makes sense.
It kind of works.
What's happening?
See there, we're moving P around. And at every point, OP is the geometric mean between OQ and OA. I don't know how to stop this thing in the middle. It'd be nice.
Right click on it, maybe?
What's that?
Try right clicking on the thing.
All right, let's see. No, no.
And then you could probably push, this was probably an option to freeze it.
Anyway, I think people get the
You said
idea.
OP is the geometric mean between OQ and OA.
Right. So this is the kind of thing that Archytas he'd be thinking about, well, how can you make this kind of motion and this kind of intersection of, is there some intersection of surfaces that would give you this kind of geometry? And so one of the things he did was say, well, what if we take this, well, we'll just look at a half, this is all we're interested in, the top semicircle. Suppose we flip that up. I mean, it's vertical on this, but if you think of it,
It's in on O.
yeah, think about, here's our OP, OQ, OB. Now suppose we have this rotating around here, intersecting a cylinder. The cylinder, at any given point where you have the intersection, the cylinder is going to make this line here. That is, if you move the semicircle around like this, it's going to be intersecting at some point, at a point that will shrink as it goes around, but it'll be intersecting this.
Oh, like if the cylinder is stationary.
Exactly.
And then the semicircle is moving.
Right. And I have some little models here that, well, we'll have a little break in a minute to look at some of these things. But this has, you can see the cylinder, and then you can see a couple of positions in the semicircle where it.
Do you have one that moves?
No, I don't have one that moves. And what's interesting is look at the point P, where the point P is. It starts out when this semicircle is all the way here. Point P is going to be at the same place that A is. And then as you move this around, point P.
So the radius of the cylinder is the same as the
Right.
radius of the semicircle.
Now I have read that that's not necessary, but I haven't really thoroughly investigated that. It's simple to make it the same, and it doesn't really lose anything for its not being more general. But if you, so you think of where P will kind of proceed, it'll go up to a certain height, and then as this goes around more, this is cutting the cylinder way off here, so it'll go down to here. So you can see the point P will make an interesting curve, and it's kind of a double intersection. It's a double curve, a curve upon a curve, because there's the curve of the cylinder, and then there's the curve of the
Torus.
the torus, right? So what you actually create is a curve on the cylinder that's what.
Like the intersection between the two.
It's the intersection between the cylinder and the torus, which was called the bold curve by, I forget what the guy's name is, the guy who kind of, Eudemus. He's the guy who essentially wrote up what Archytas had done. So we call this curve the bold curve. And
What
this
language was that in?
Greek, I think. Here's another example of it. I got the bold curve is this curve here. So, so the key thing now is to find out at what point will, if as you rotate the semicircle, at what point will P and Q and B line up precisely so OB is half of OA. So why don't we do this? Why don't we take a short break so people can look at these models, but we should get back on it at 9 o'clock, so we got 7 minutes, I guess.
Okay.
Okay?
7 minutes.
So there are a number of these models that have different aspects of the process.
You said the
Did you
bold,
put these all here, together here, Hunter?
No, I made them down that way.
Hunter, where'd you say on this one, the bold curve
The bold curve is the.
This will have a bold curve.
Is this a coat
And this
model?
is the intersection of the
You
Torus.
wanna make one?
And so,
That one's kinda neat,
This
it's
is
cute.
Yeah, I like it,
Right.
I like the coat model.
cylinder here.
It's a good idea.
So they intersect.
He sanded it down too.
Wouldn't they keep intersecting them?
well, they do. And here's one, and then if you think of between here and here, it goes all the way down from here down to 0.
Right.
But at this point, the P will be in the front.
Oh.
So it'll
So
make
it just
sharp.
goes, that's the
Yeah.
full.
So it goes up slower than it comes down. It comes down.
Oh my God.
And
This
so
one
any,
has a cone on
so
it.
you wanna get pinpoint P here, basically.
Well, wherever it's going to be, such that
Oh, we still haven't figured that.
we haven't figured that out yet.
Right, but we just know it has to be somewhere.
Right, somewhere along there.
This one's more like mine. I like the cone actually. This one's a nice one.
Yeah, that's got.
I don't really see the importance of the bold curve. I guess it's just the two surfaces, huh? The bold curve is just, the point is that you have two surfaces creating the line
Right,
that you need to get at that point.
right. Somewhere on that line is the point you're looking
Yeah,
for.
yeah. I guess that's.
How do we
that's why.
know which point it is?
That's what we
But yeah,
point
I
out
like
in
this
the last
one.
section.
'Cause it doesn't, yeah, I like this one.
As you might suspect, it has something to do with the cone.
I don't know.
You don't really
This model
just-
has a cone.
You don't really need to map the whole cylinder, really, you know?
So this is the cylinder here,
Yeah, this is the cylinder.
this circle
Yeah,
coming, and then coming up
yeah.
out of the surface, and this is the torus.
So Leonardo, we're looking at the
So the two intersect.
the models right now. We'll be back soon. Actually, Victor, why don't you look at it here, and then Leonardo could at least look at that one
Specific color.
while you're
Well,
looking at
we
it.
don't have the cone yet. We're gonna do that one.
Alright,
Put that down.
how does,
Right.
break
Oh, here's the cameras here.
Shouldn't it to show her?
Yeah, just
Is
face
there a way
it.
where I can see what he's seeing?
Not the way I have it set up right now.
So right now, you're just trying to,
Hold it down. Yeah.
right now, you just want,
Where's the bold curve on this one?
you want people to get a sense of,
These
Imagine
points.
it.
It's just the.
I guess you can say the
Yeah.
interplay between the torus and the cone,
Right.
so that one can orient one's mind to where one would need to put. Here you designated this Q on the two-dimensional surface.
Right.
It's not actually drawn on, it's actually physically.
Oatmeal box.
Oh, I don't think I
Let me see the oatmeal box one. Yeah, I like this one. This one's nice.
saw. Oh, it's cut out.
Yep, instead of actually, I think it goes from there.
Actually.
Like he was saying, it goes up more slowly and then it drops.
Quickly.
Yeah.
Can I talk to him?
Sure.
Hey, Leonardo, can you listen? Can you hear me? Is that the mic?
Yeah. Oh no, it's I think on the computer. Leonardo, are you there?
I've got a question for you.
Maybe he's taking a break.
Are you-
What?
I don't-
No.
What was the, I see, the diameter of this cylinder
Uh-huh.
was chosen as the radius of this?
Exactly. Yeah.
Okay, I got that.
Which, as I said, I don't think it has to be, but it's convenient that it's that way.
Well, oh, so it doesn't have to be any relationship to it?
As I say, I haven't fully investigated that. I think it's kind of puzzling how it would work if it were bigger, but.
It seems like it's just because of the way it's set up. Like,
In this particular
Yeah.
one.
If you changed,
the size.
like if you changed the size of this,
Do you see what?
or changed its orientation.
It's interesting.
it would be
Okay,
different.
this
Not really.
This was-
rotates on this axis.
It would be
Create
similar,
the-
but I think the main thing is that they both intersect.
How we're getting that third
About this
Cylinder.
one.
Yeah,
third
because the
factor
torus
of
is
cross section.
rotating about
Oh,
this
yeah,
degree.
because that's the center
So there's like
of the
three,
torus.
like, I guess you
Yeah.
can.
What are you rotating?
Reverse,
I'm
so
saying, this,
Explosion.
this,
Whereas, like, if
this
was, like,
particular
if
arc
you
this
have to have
cylinder was just
three-
following the
would
outside
be
of
the
the
arc
torus,
of the cylinder
found that proportionality
of our arc of the cylinder.
Which are
third,
very
third dimension. So here what you're
Oh.
seeing is this here, I think it's rid of this on Friday, so if you continue on motion for Friday, and it's trying to show you that.
Either one of these, if they were held,
Shape.
The white.
this one,
Uh-huh.
This is you.
this is,
Like
Oh, I
this.
see.
if it's rotated
You rotate it right inside the
And
cylinder.
then here, along this point.
from where it is, yes.
Rotates it like
Right.
that, and then creates a.
Yeah, create a
So
sphere right
But
inside the
now,
cylinder.
we're not creating a, what is this object?
Yeah, and we're not, yeah, we jumped it.
Constructing.
Well, if you continue this process
I don't understand how you.
of moving this around,
Yeah.
semicircle around, you create half
Where
of
do we
the,
put
the
Q?
top half of the torus.
Because you can see that there's
Top
motion.
half of the torus.
Potentially.
I mean, think of the
Oh.
whole, if
You can
this is a whole
these
circle
things
going down
moving
below
around,
this.
right?
Think of a whole circle
So
rotating
we determine that,
around this,
we figure out where Q is here, then we can figure out where
all around.
that third
You got complete donut.
factor.
Okay, well,
listed
you've
would
got
be.
several, you've got one that, which is constructing, is rotating on this
To
point,
give validity to the previous two
creating this
geometric means that we've already found
circle.
with the
Yeah.
similar triangle.
But then, that object,
We need to determine where to put Q. But now it's out of the realm
Oh,
of.
no, that's-
two
oh,
sets.
yeah, then that
Around
object-
Three different.
then rotated on this,
Axis.
axis. Is that the, would that create that, what is a torus?
Torus, oh, I don't have, I should have brought my little slinky. Remember slinkies?
Yeah,
The little spirals.
Yeah.
See, if you just take a piece of slinky and wrap it all the way around,
uh-huh,
you'll get a tube that's circular, right?
okay,
That makes a torus.
I see. Okay. Hmm.
So, we should probably get back to business here. We're
All right,
doing all right. So, the bold curve that, the bold curve here is, as people are seeing, is the intersection between the torus as you rotate this and the cylinder. Now, at each point, you have a different ratio or growth factor. You know, remember when we were talking about the growth factor and doing the cubes, and then we had the one of 1.2. At each point, you have a particular ratio. Like, you know, any of these, it will come out to a particular number, the ratio of the lengths. So at every position of P, there's a particular ratio, particular growth factor, which is, if this is 1, then OQ is that the length you know, the length of OQ defines that growth factor. So as you move around, it's confusing. As you move this around, then the actually, where's the one? Yeah, this one. You know, you can see all the ratios of the triangles will change. At any given position, the triangles that we've looked at will be similar. But as this moves, intersects at the cylinder in a different place, the ratios will be different. So the key is to find the point where that ratio is the one we're looking for. So this is the kind of thing that Archytas was looking at. And he had, get back to my original notes here. Okay. So let's just review a little bit this idea of these proportions and the growth factor, because we're getting close to what we're really interested in. You know, one thing that Archytas would have done is I said he might have extended this up to look at this. He might have extended this further down this way from the perpendicular there. And we'll call this R. And again, you have a similar triangle. But let's look at something different. Let's look at the one where we have the you know, this circle is vertical compared to this one. So you have OQ down on the bottom here, or yeah, OQ to here. OP is up this way, right? Okay. Leonardo, are you back? Hopefully you can see. Anyway, so on our, let's do something a little different. Let's look at this circle on the base, the horizontal circle.
The cylinder?
Did I say cylinder?
No,
Oh.
I'm asking.
Oh, okay. What about it?
You said the circle on the base, so you're talking about the cylinder?
It's the cross section of the cylinder. Yeah.
Right.
Yeah. So here we are. This is the cylinder and the cross section. Here's O and here's A. We've got our line moving around, or our semicircle moving around like this and intersecting this. It intersects it at Q, right? People follow that now? This is the one on the horizontal one. You know. Now suppose we draw this perpendicular. Actually, that's R. That other thing was not R. This is R. Now, we have some similar triangles here, right? We can look at this length compared to this length compared to this length. OR is to OQ, as OQ is to OA. Now,
You're just projecting, you just took Q and projected it down onto the...
yeah, see with these, this semicircle we were looking at before is the one that's up in the air, the vertical one.
Right.
But what we're now going to look at is what is down on the
It might be
on the ground.
helpful to just extend OQ to A. You know what I'm saying?
Oh, out here?
Yeah.
Yeah. That's a good point.
Because
Oh, but
otherwise
that's
it's a little confusing.
But that's a different A, that big A there.
It's the same
just
A, but
rotated.
it's
No,
Oh.
that's A right there.
yeah. You can call this A sub 0, and if you extend this out, so this is the same length.
Yeah, it makes sense. I thought it was the same A at first, and so I got confused. But yeah, A
Okay.
sub 0.
Yeah, we're rotating this like that. And so this is Q here. But now, see what what we have here is a different, this is not the growth factor that we are actually using. This is something different. Because how is OQ related to OA in our original ratios? Remember we had OB is to OQ.
Well, we're missing our P.
Yeah, we don't have P in here now. OQ is to OP as OP is to OA. So from OA to OP, you have to shrink it once. Or to go from OP to OA, it has one factor of growth. To go from OQ to OA, you have to have two factors of growth. You follow that? That is, I mean, you remember when we were doing the 1.2?
Yeah.
If that was our growth factor, to go from OQ to OA, it's 1.2 times 1.2. To go from OB to OA is 1.2 times 1.2 times 1.2. Or if you want to think of it the other way, for some reason I find it useful to think of it as shrinking it. So you start with OA, and you shrink it once, and you get OP. You shrink it twice, you get OQ. You shrink it a third time, and you'll get OB. What about OR? How do you get OR?
In terms of this diagram here.
Yeah, in terms of, yeah, and what we're you know, what's the best way to put it? Well, let's look at what it isn't. You remember how we got OB, right? And B, to get B, OB, you could say you have to shrink OA 3 times. Once to OP, another time to OQ, and another time to OB. Okay, so it's 3 shrinks away from OA. Now,
Needs a lot of help.
yeah. I mean, if OP is, let's say OP is 80% of OA, let's just as a percent of OA, then OQ is 80% of OP, and OB is 80% of OQ. So OB is 80% of 80% of 80% of OA, right? Because you basically is multiplying the shrink factor by itself. So in those terms, what would OR be? Suppose, let's say it is 80%. Let's say to go from OA to OP, you have to shrink it 80%. To go from OA to OQ, what do you have to do? Yeah, 80% times 80%. 2 shrinks away. What about from OQ to OR?
80% of 80% of 80%.
You're saying 3 shrinks away from OA?
Yes.
Well, how does OR compare to OQ?
Same way that OA compares to OQ, or
Yeah, right. Now this, to get from OA to OQ is 2 shrinks.
Yeah.
So to get from OQ to OR is 2 shrinks. Because it's proportional, the same ratio. So OR is 4 shrinks away from OA. OP was 1 shrink away, OQ is 2, OB is 3, OR is 4.
What is the figure that we're looking at to get that? I don't see it in this.
It's a little confusing because before we had on the board this semicircle with OP,
Yeah.
right? Now we're looking at the one that's down here, where Q is here and R is here.
I see.
Now the reason why this is important will become clear
But
soon.
A sub 0 is not the same length as A1.
Yeah, it is the same one.
It's the same.
Yeah. See, we're just moving this around. But this
So
were.
it's like you just.
That's what you see in this one. You can see the. It doesn't have them labeled there. See, now Archytas would be looking at this, and he would say, "Uh-huh." He would see something that most of us wouldn't likely see without a little bit of help. But he sees the solution to the problem. It has something to do with R. Oh, that's why you put it up there. It's not just arbitrary. Because if OA, in a sense, the distance between OA and OB is 3 shrinks. The distance between OP and OR is 3 shrinks, right? Now look at this. You have O and P and Q and R down here.
So you just took that triangle and folded it down onto the.
Yeah, we haven't gotten to the triangle
No,
yet.
but the triangle that is on there, you just like folded it down onto the plane.
No.
Oh.
See, this is a different.
It's just
This
a- it's just a
triangle.
different triangle.
This triangle is skinnier than this one
Okay.
because this one is. It's 2 growth factors.
I can see that. I'm just
Yeah,
having a hard time
yeah.
visualizing it.
Let's see. There's a small version of this. Where's the small version?
So this is the triangle that we're looking at now. The O, Q,
Uh-huh.
and this is R.
No, R is here.
Oh, there. So O, Q, A
Uh-huh.
is the triangle. we're looking
Yeah, I
at.
didn't have that one.
Okay, but that line should be there. And then this is R.
See, this is a wider angle than this one here.
Okay, so it's not.
It's not the same.
Yeah, but you're saying that the relationship of R2 here is the similar growth proportion.
I'm saying that, the relationship of OR to OQ is the same as from OQ
Q
to
to OB.
OA.
Mm-hmm.
But then the relationship between OR and OP is going to be the same as the relation between OB and OA. Because they'll both be 3 shrinks
Could you
away.
maybe write it in the proportion
Oh,
like you
it's
did
the same
that?
radius.
So then does that mean that OR
OR
OB is
is to
OB
OB.
is to
Yeah.
Q?
Yeah. I'll put it in parentheses because it's not exactly in the diagram in kind of the same way that these others are, but it is fact is the same.
But it is the same.
Yeah, it is the same proportion. We just generated OR directly from OQ without going through OB. But don't get confused by it. The important thing is that at each step between, at each step, these are the same ratios. Same growth factor, same shrink factor. But see, remember, the critical one that we want is between OB and OA, right?
Yeah, I guess I'm just wondering why now you're bringing in this other, the OROB.
Yeah, it does seem kind of arbitrary, doesn't it?
We already had the setup to find, seems like what we're,
As far as I know, Archytas would just be playing around with these things.
yeah.
Yeah, he would have extended this one up to, or with the original one, with the P. Extend it up so he has a vertical, and then. But the key thing is that he keeps in mind this idea of the original diagram that we had. With O, A, P, and Q, and B. And the key thing, he's got this idea in his mind, this intersection of the torus and cylinder. This is the sum of all the positions of P. And he's trying to find the position where this OB will be exactly half of OA. And he would have noticed, OB is 3 shrink factors away from OA. And the fact that OR, when you put that in there, it's 3 shrink factors away from OP. And that gives you something very, very crucial. And we have a couple of these. Yeah, that one over there that Michael has this OR on the bottom. You can actually let me use that one because it is a bit bigger for people to see. So here we've got our usual O, P, Q, O, A, and OQ. So what Archytas would have said, and this is his insight, he's thinking about these solid creations all the time. So he says, well, what happens if you put a triangle between OP and OR? That is one that's not in this plane, not in this plane, but it's one angled in there, like this. What we just demonstrated is that the ratio of OR to OP is 3 shrinks multiplied by each other. But this is a triangle, and triangles are fun to work with, right? Because you can think of a triangle that would have that this length would be exactly half of this length.
What?
See, what we're think again what we're looking at. We want to find the OB that's exactly half of OA. And we've just discovered by making this R that the relationship between OB and OA is exactly the same as the relationship between OR and OP. You know, it's 3 factors away. So if you think of this geometrically as a triangle that's put in here between O, P, and R, then we have this length is exactly half of this length. Or actually, you could, not in this particular, you could create a triangle, or you can imagine a triangle, which would have that kind of relationship. And if you can find that kind of relationship, that particular triangle, then you've won the battle, because you've got your ratio of, if this ratio from here to here is 1 to 2, then your ratio of OB to OA is going to be 1 to 2.
Is there any way to do that just based on selecting a triangle, or?
Exactly. That's what you do. You select the triangle and you rotate it to where it intersects the bold curve. Because the bold curve is all the points P that solve the, what you want. So you needed to find that critical factor that identifies the particular point.
Why couldn't you have done that in your model?
Why couldn't you have done what?
Why couldn't you have done that in your model? You're saying it's a hypothetical triangle?
You mean in this one?
When you construct it, because it's not the case that
Oh.
that is half.
I could have.
You could.
Yeah. See, and that's an easy triangle to do, because if this length is 1/2 of this, that's a 20, 30, 60 triangle. I mean a 30, 60, 90 triangle.
Okay.
Because the hypotenuse is twice
Yeah.
one of the sides.
You could do really construct, you could bisect it on it.
So, Archytas probably would have been looking at this not unlike the way, Mozart would be looking at a musical composition. He'd be playing around with these themes, and all of a sudden it kind of gels together as a unit. And so he's playing around with these ideas, and this idea of the, he's looking for this 1 to 2, relationship. So he's just kind of playing around with these things, and this one just kind of pops out when you do the OR and look at it in comparison to the OA, or in particular to the OP, because then you've got 2 means between the 2 extremes. There's some other video presentations. Oh.
Yeah, he got off.
You got off, okay.
Yeah. You had to go.
All right. So I guess we'll just exit out. Okay, so we can look at these other pictures here. There you can see the it's got somewhat different labels there. Instead of Q, it's called, what's that?
C4 would be R.
Exactly, yeah. And P2 is Q. And then we'll look at the next one here. There you have it with the triangle inserted in there. In that case, the triangle is pretty close to, I think, to a...
Yeah, it's a really
1 to
steep
2.
triangle.
Yeah,
It's-
yeah. And let's see what else we got here. Oh yeah. This has 3 different ones. But again, showing different kinds of triangles there. And the bold curve.
So the base, this is obviously the torus, the top curve, and then that bottom curve is the cylinder, base of the cylinder.
Yeah, the bottom is the base of the cylinder. Oops. This is the bold curve, which is the intersection of the cylinder and the torus. This is sweeping, the gray semicircle is sweeping out the torus.
Yeah. But the radius of the cylinder and the torus don't necessarily, you were saying, have to be the same.
That's what I read somewhere. I won't vouch for it. I haven't.
Because in that picture, they don't look like they're the same, but maybe that's just.
Oh. Yeah, it's true. It's hard to tell exactly. Looks like the semicircle's bigger.
Yeah.
And let's see, I got one more here, I think.
Where did you get the root?
There's a.
Oh, it doesn't matter what, no. I just realized, you're right, it doesn't matter what size
The cylinders? Maybe it just has to be smaller.
yeah.
Because, I mean, obviously the semicircle has to intersect it. No, actually, a lot of this there's an article in the Schiller Institute site by Fletcher James. Which is called Archytas' Musical Construction. And I guess he has the diagrams. I forget where I got. Yeah, he's got the figures. I guess they're links in the article. So, I don't know. Is any?
Could you put that just on the first page, the one with the C4?
Yeah. I think that's this one. Yeah. So, any questions or?
Can you explain again what you were saying about how Archytas, when I thought about it, would be the fact that you had the 3 shrink sizes away, both on the torus semicircle as well as on the cylinder semicircle, and how that would have clicked in his mind that there's some kind of proportional that can be drawn between them.
I mean, it's the best I know. I mean, I just tried to. I mean, I think he would play around with these different things, and you know, why he would come up with the R. I mean, he was probably looking at the model without the R. You know, with this Q, he's looking at the horizontal and the vertical, and there's Q. Probably just seems like a natural thing to do. Say, well, what happens if I draw that perpendicular there? Or maybe he had more of an insight into. I mean, obviously he was thinking about where how do you find that point on the bold curve? And I don't know, I guess that's about as much as I could say of what might have been going on in his mind.
So you're saying that in terms of the final ideas, OR is to OP, and OP is to OQ, as OQ is to OP, as OP is to OP. Those are the 2 ones.
Yeah, and when the critical ones are between OB and OA, and between OR and OP. The fact that those are the same is what's key to solving the thing. The ratio OR to OP, you can actually write it down if you want.
The ratio of OB to OA is the same as the ratio to OR to OP.
OR to OP is the same as OB to OA.
So therefore, if you know that OR to OP is 1 to 2, you know that OB to OA is 1 to 2.
Right. So, working on this is part of how to become a better apprentice of the Creator. As Len recently talked about it. And, you know, what he's been doing, you know, you think of the work he's done with the basement on the Kepler and the whole, you know, youth movement, working through these things, is developing that way of thinking about the organization of the universe as a whole. And so this is a small step in that direction of the ongoing mastery of how the universe works. So, any other?
Could you, give us the next one?
The second one? Sure.
And C2 on there, well, actually, I guess it's on the previous diagram, maybe C2.
On the previous one?
Yeah,
That was the same as, that was Q.
which was the same as P.
Yeah, for some reason it's got P here and P here.
P2. So P2 and C2 are the same thing. It's just one's on the.
Yeah. I mean, that's why I actually did my own kind of notation on this, because it was a little confusing.
So there you have P2 and C2.
P2 and C2, yeah. In his article, he goes through it a little bit differently.
Yeah.
But it's the same idea.
But yeah.
There's that one. So you better remember all this, because if we got a plague spreading, we may need to double the cube.
Plague of oligarchism.
Plague of bankruptcy through the cities in the United States.
So anyway, that's all I got.
Yeah, he gave us something to chew on for a while.
Something to chew on. Well, I do recommend this article. It's actually very well done, because he's
It's on the Schiller Institute.
Yeah, Schiller
It's
Institute.
called the.
called Archytas' Musical Construction by Fletcher James. There are also some Riemann for Anti-Dummies articles on this a few years ago.
I might have like a whole folder of stuff on my computer. Because I did it a few years ago and I've like looked at all those articles. Just
Yeah.
try it out there.
Yeah, I have actually have a little folder with a bunch of those. The Riemann for Anti-Dummies that relate to this.
Do you know anything about the screwer? Supposedly there was something that people figured out a few years ago about there's actually a sphere involved in this as well, which is implicit?
What I do know is that Pierre Baudry was working on something, and I mean, he had a whole new hypothesis about how it was developed. And but I think there's at least quite a bit of controversy over whether that's true, or maybe even more definitive. I mean, Susan Kokinda was not so convinced that, I mean, she was saying it was kind of off, but I don't know, it was kind of intriguing when I looked at it, because he went through this thing about the building, construction of the pyramids, and how they had I don't know, some of the ratios of angles in the pyramids were, it kind of gave an insight into this. But I don't know. I didn't work through it in detail.
It's really hard to put sugar cubes back in a box. I think we should just eat them.